Thank you for watching my videos and encouraging me. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We now discuss the solution of a problem from the section Complex Analysis that appeared in the CSIR National Eligibility Test held on December 15, 2019. The question is related to identity theorem. The question is from Part C, which is a multiple select question. There can be more than one answer, and the question carries 4.75 marks. And the question ID is 879-801-822. This question is suitable for all these examinations. Right. The given question is, let F is a map from the complex plane C to itself, and it is an analytic function. Let F from C to C be an analytic function. For Z0 belongs to C, which of the following statements are true? We are given four options. Option 1, F can take the value Z0 at finitely many points in 1 by n, where n belongs to n, the set of natural numbers. Option 2, f of 1 by n is equal to Z0 for all n belongs to n. This implies f is the constant function Z0. Option 3, f of n is equal to Z0 for all n belongs to n, implies f is the constant function Z0. Option 4, f of r is equal to Z0 for all r belongs to Q, the field of rational numbers, intersection closed interval 1 to 1 comma 2, implies f is the constant function Z0. Right. We now discuss the solution of the problem in detail. We have f, a map from the whole complex plane to itself, be analytic function. When it is an analytic function on the whole of C, it is called an entire function. Yes, f is an entire function. We are given a Z0 belongs to C. We call on option 2, f of 1 by n is equal to Z0 for all n belongs to n, implies f is the constant function Z0. Yes, we have recognized this one, and this can be done by the application of the identity theorem. So let's be very clear about the identity theorem and how it is to be applied, and I will show you. Right. Define a function g from C to C by g of z is equal to Z0, where Z0 for all z belongs to C. So there is a print mistake, Z0 is extra, and for all z belongs to is missing. Anyway, so why we want to show that at the end f is the constant function. That is why g we have taken and we have defined it as a constant function, and it is taking Z0 value for all z belongs to C. Agreed. Now it is an entire function. Why? It is a constant function. Right. Let us define another function h of z as f of z minus g of z, and both f of z and g of z are analytic, are entire functions. H of z is also an entire function. Agreed. Now h of 1 by n is f of 1 by n minus g of 1 by n. F of 1 by n is z0, and g of 1 by n is also z0 because it is a constant function. Z0 minus z0 is equal to 0 for all n belongs to n. Agreed. So that means h is vanishing. H is vanishing at every point of 1 by n for all n belongs to n, and that means we have a set of zeros of 1 by n. What are the zeros of 1 by n? The zeros of h. The set of zeros of h. What are the zeros of h? 1 by n. N belongs to n. So now let S be the set of zeros of h in C. That is, h is equal to 1 by n, n belongs to n, is the set of zeros of h in C. And this 1 by n tends to 0 as n tends to infinity. And not only that, and 0 is the limit point of 0 in C. Limit point. Limit point of 0 in C means every neighborhood of 0 contains infinitely many points of S other than 0. Agreed. 0 is a limit point in C. Agreed. And let's now recall the famous identity theorem or uniqueness theorem. And it states, suppose that f is an analytic function in a domain. Here domain means connected, open connected domain, open connected set. So it's a domain, the connected domain D. If S is the set of zeros of f in D and has a limit point z star in D, then f of z is identically equal to 0 in D. So using this one, we will say by identity theorem, h of z is identically equal to 0 in C. Our domain in our context is C. Agreed. So that means h of z means f of z is equal to g of z for all. H of z is identically equal to 0 means f of z minus g of z is identically equal to 0. That means f of z is identically equal to g of z. So f of z is equal to g of z. And what is g of z? Z is equal to z naught on C. So thus f of z is coming out to be a constant function that sends every element z belongs to C onto z naught. So that means f is the constant function z naught. Agreed. So thus the option 2 is true. Agreed. Move to the next options. Let's take option 1. F can take the value z naught at finitely many points in 1 by n in the set consisting of 1 by n, n belongs to n. Right. Yeah, this can happen. We can find out a function which takes the value z naught at finitely many points of this one. Okay. So let f of z is equal to e power z plus z naught minus e for all z belongs to C. It is an entire function because e power z is an entire function. These are all constants. So it's an entire function. Right. Now f of 1, when n is equal to 1 value it comes. F of 1 will be e power 1 is e plus z naught minus e. E cancels and comes out z naught. So f takes value z naught at a point 1 belongs to 1 by n, n belongs to n. And further, for any other 1 by n, n not equal to 1, f of 1 by n is e power 1 by n plus z naught minus e is not equal to z naught. Is not equal to z naught. So that means f of z is not taking the value z naught at any other point except at 1. So f is taking the value z naught at finitely many points of this set. So f can take the value z naught at finitely many points in this set. So the option 1 is true. Right. We move on to the option 3. F of n is equal to z naught for all n belongs to n. Oh, this time it is taking the value z naught for all natural numbers n belongs to n. Then f is a constant function z naught. Okay. So consider the function f of z is equal to z naught plus sine of pi z. It's a non-constant entire function. It is not a constant function. Z naught is constant. It's not a constant function. Therefore, it's non-constant entire function because sine pi z is entire. Z naught is a constant, being it is an entire. The sum of an entire function, sum of two entire functions is again entire function. Therefore, it is a non-constant entire function. Now, for n belongs to n, what will be the value? F of n is equal to z naught plus sine. For z, you have to substitute n. Sine of n pi. Sine of n pi is 0. It comes out to be z naught. Now, so that means f of n is equal to z naught for all n belongs to n. N belongs to n. But is it a constant function? No, it is not a constant function. So, but f is a non-constant function. That means the option 3 is not true. Agreed. Agreed. Move to the next option. Option 4. F of r is equal to z naught for all r belongs to q intersection the closed interval 1 comma 2. Then f is a constant function z naught. Yes. Yes. We have f of r is equal to z naught for all r belongs to q intersection the closed interval 1 comma 2. Right. For all those rational numbers in 1 comma 2, closed interval 1 comma 2, f of r is z naught. Define g from C to C by g of z is equal to z naught for all z belongs to C. It is an entire function. Being a constant function, it is an entire function. Let h of z is equal to f of z minus g of z. Let us take S belongs to Q intersection 1 comma 2. It is a rational number. It is a rational number in the closed interval 1 comma 2. So h of S plus 1 by n. Now S belongs to Q intersection 1 by 2, the closed interval 1 comma 2. S plus 1 by n also belongs to that. H of S plus 1 by n is equal to f of S plus 1 by n minus g of S plus 1 by n. Now f of S plus 1 by n is 0, is z naught, is z naught. And g of S plus 1 by n is z naught, being a constant function. So the difference is 0 for all n belongs to n. So that means we have found S plus 1 by n is a 0 of hz. So who are the zeros of h? S plus 1 by n, the set of all S plus 1 by n. And S is a limit point of the zeros of h. So let S be the set of all S plus 1 by n, n belongs to n, is a set of zeros of h in C. And every neighborhood of S will contain infinitely many points of capital S. Therefore, S is a limit point of S in C. In C. Right. Because C is the domain of a connected domain of all these functions. Right. So we recall identity theorem, we have already seen. So by identity theorem, h of z is identically equal to 0 in C. That means f of z minus g of z is identically equal to 0 in C. That means f of z is equal to g of z is equal to z naught on C. Therefore, f of z is equal to z naught on C is a constant function. So f is the constant function z naught. Right. Thus, the option 4 is true. Right. The answer to this question is options 1, 2 and 4. Option 3, which we have seen, was not true. Right. That is the detailed discussion of the solution of this question. And it's a beautiful application of identity theorem. And it is also an interesting question. And this is not difficult. This is not difficult. If you are familiar with this identity theorem or uniqueness theorem, I think you can do it very comfortably. And an observation of all these question papers of CSIR National Eligibility Test tells us that the identity theorem or uniqueness theorem is very, very important, and many a times its applications are coming in the exam. So learn identity theorem, uniqueness theorem, and prepare a very good notes on it, and gather all those questions that have appeared in the CSIR NET examination and solve them and prepare a good notes. And before going to the examination, just glance through it, and you will be successful in the exam. I am sure that you have understood the solution of this problem. Thank you for watching the video now. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. I hope to meet you once again in another episode of learning. Now keep learning. I wish you all the best. Thank you.